Now you can go.
So, hello everyone. It's my pleasure to introduce Horacio Andrés Petit. I met Horacio actually 7 years ago, almost exactly, when I went to Bahia Blanca in Argentina to teach a course, 1 week long course. And among the students was Andres was there, as we call him. And by far, he was the most interested one. And he had just completed his PhD back then. And it was the first contact we had. So I was very impressed by how keen he was and how knowledgeable he was. He's chemical engineer by training in Argentina, and he did his PhD in air classification, basically CFD, DEM, modeling of air classifier. He has patents of air classifiers. So when I met him there, uh, one of the outcomes of the course is that I immediately invited him to join my group. So he became a research fellow for these last 7 years already in my group in Brazil. At the same time that he's a, a researcher in Argentina in CONICET, which is the biggest research center, and he's located in the province of Buenos Aires, Argentina. So, in spite of the rivalry between Brazilians and Argentinians, those of you who follow football, he really got along very well with all the team here. So he's a really a valuable player in our team, I'd say. So we really, to the level that we invited him to become an associate member of the GCC. And one of the reasons is exactly of his knowledge of classification. But if you look at his application since, he has been involved in modeling grinding, and he's really knowledgeable with of a variety of tools that we have been using these days, including CFD, DEM, SPH, breakage modeling, and everything. So we actually suggested him to come to today to talk a little bit of dry classification and really to put the word out in a topic that we all have been more and more interested in these recent years. So please, Andres, the floor is yours. The floor is yours.
Good morning, everyone. Thanks, Professor Tavares, for the kind words. And it's been a pleasure to work with the team of in Rio de Janeiro all these years. Without further ado, just to check everyone is just seeing my screen, right? And hear me okay. So I will start to speak a little bit about air classification. So it is just another unit operation in the mineral processing. And it is just a separation of mixtures of ores or powders according to specific particle properties. And classification is always generally made by mechanical means, such as you have different processes such as sieving, wet classification, or dry classification. And you use sieving when you want high throughput and a simple operation. And it has good performance for cut sizes in the order of 1 millimeter or above. However, if it presents a low performance for cut size in the micrometer range. So you then migrate to wet classification that it has good performance and good sharp cuts and cleanliness of products, but usually involves more equipment if you want to reuse water. So, and of course, it cannot be used with sensitive materials. And that's why I think wet classification is most commonly used in the mineral processing, but not in food processing or in pharma industry. So that leaves us with air classification or dry classification, which uses air instead of water. And it has a good sharpness or decent cut size and sharpness of cut. However, it is more affected by fluctuations of the feed rate or particle-particle interactions. However, it doesn't require fresh water, and the products are ready to use and ready to be handled. The most common utilization of air classification is in the same way that dry classification is in the same that wet classification, and it is to complete the milling circuit. So there you can control the particle size distribution of the circuit and optimize the energy and the throughput. And just to illustrate two examples that are common in the cement industry, you have the all-in-one solution, which is the vertical roller mill here on the left. And you have the ball cement circuit, ball milling circuit in the cement industry, in which in both cases you have a crusher or a mill, and the outlet goes to an air classifier, which returns the coarse product again to the crushing or milling device to optimize the output. A totally different utilization of air classification is as a heat exchanger in some cases. Again, in the cement industry, you have this precalcination tower, which you feed the tower at the top with the material you want to send to the furnace or the kiln. And there you let it fall in a countercurrent scheme with gas, hot gas coming from the kiln. And in that way, air classification, in this case, is cyclone classifiers, gives you a high surface contact area. So it is a very good heat exchange unit that you can use to pre-calcinate particles. So how air classification works? It is based on the acting of different forces on a particle immersed in a fluid. In this case, it's air. So the dominant forces are, of course, gravity and drag. You may also use lift or consider lift and buoyancy. And of course, you have other forces or interactions like particle-particle interactions or adhesion or cohesion forces. So you can engineer a device, an classifier device, in order to have these forces acting on opposite directions. Just to illustrate or give you an example, this is a zigzag classifier. And in a laboratory scale, you feed the particles here, in this case it's iron ore, at the top, and then you pump a flow of air upwards. So particles fall and the air is going up. If you take a minute to look at the particle located here in the orange dot, you may see that gravity is acting in a down direction and drag in the up direction. So fine particles are dragged by the air and go up with the air, while coarse particles go down to the bottom. So you have a fine product and a coarse product of the classification. I use this nomenclature instead of overflow and underflow, which are inherited from the wet classification. So how do you describe the performance of an air classifier? For each particle size, you will have a probability to go to the fine product or to the coarse product. So if you sum up all the probabilities in the range of particle sizes, you will have a partition curve. Ideally, the partition curve is this one here in green, which is a step curve. So from a critical size, particles coarser than that size will go to coarse product, while particles finer go to the fine product. And that size is called the cut size. And it represents the particle size, which has a probability of ending up in the coarse or the fine fraction, equal probability of ending in any of the fractions. However, real curves are not as ideal, and you have two examples here in red. You have this sigmoid curve, which is quite common. And at the cut size, you have a slope. And that slope is called the imperfection or the sharpness of the cut. And it is telling you how selective the classification is. Also, you may have this increase of fine particles, increased probability of fine particles going to the coarse product. And it is called the fishhook effect. And it is quite common in air classification. And it is the outcome of adhesion or disturbances in the flow. In terms of energy consumption, you can describe the air classification in terms of pressure loss. You can measure the static pressures at the inlet and the outlet of the classifier. And the difference will tell you how much energy you require to pump the air and the particles inside of the classifier. Bibliography tells you that this is the common way to describe energy consumption in the classifier. However, I think you should consider also the auxiliary equipment, because air classifiers are not a standalone unit. They usually require different auxiliary equipment such as bucket elevators or conveyor belts and so. So the energy required to lift the particles or the feed up to the feeding point is usually in the same order of magnitude of the energy consumption of the fan in these cases. And there are many designs of air classifiers. Just to name a few here, perhaps the most commonly known is the cyclonic classifier, and perhaps the oldest. It is basically a cylinder and a cone where you have a tangential inlet of an airflow, creating a centrifugal force field. So here, fine particles are dragged inwards, and coarse particles are pushed outwards to the outlet of the cyclone. And you may have also more modern classifiers, such as the inertial classifier that we will talk later, or you may have dynamic classifiers. So dynamic classifiers are classifiers which have moving parts, and they have rotors or cages inside of them, which create the airflow. Dynamic classifiers usually are divided into generations, which you have the first, second, and third generations, each one improving the performance of the previous generation. So as I said, generally the air classifier is not a standalone unit. You have the primary air classifier where you want to cut your particles. So here you feed your particles that are going to be classified and the main airflow. And generally that will give you the coarse product. Fine particles will go to the auxiliary air classifier, which is a secondary unit. And the main reason of this secondary unit is to dedust the gas, the air, and extract all the greatest amount of particles previous to go to send the air to the back filter. If you don't do this secondary air classification, you end up with the problems in the back filter, or also you may have a very big filter, which is it is quite with the high cost. And how do you model air classification? The most common way is to use computational simulations. However, you may go to phenomenological models or empirical models, however, but in latest years, everyone is using this type of simulations. So the typical use of computational methods is to use an Eulerian Lagrangian approach, in which you have two phases, the air and the particles, and the air can be solved using CFD solvers, and solid particles may be solved or simulated with DM or DPM methods. DM and DPN are quite similar methods, but DPN is like an oversimplification of DM, which DPN does not account for particle-particle collisions or addition forces or volume fraction of the particles in the air. And of course, you need to couple those methods and consider air-solid interaction in order to have the full picture. So you solve the CFD as part of the airflow, then you inject particles and track the trajectories, and you can count where each particle is going, and you can sum up and have the partition curve. Another approach is to use a full Eulerian approach, in which both phases are considered continuum phases. So both the air and the particles are considered Eulerian phases, and you can solve them both in a CFD solver. The downside of this approach is that you require one particle phase for each particle size. So if you want to compute the partition curve, it is not straightforward. You need several phases, and usually the solver will have diversion or numerical problems. So after this brief introduction, I just will illustrate air classification with two main cases of study. As Professor Tavares said, I did my PhD in Argentina, and it is a region where Buenos Aires province here, it is a region where there are a lot of quarries, small quarries. They produce coarse aggregate for concrete, and they crush granite and dolomite. As a side product, they obtain the fine part, which is what they call a sand. And the top size could be 3 millimeters or 6 millimeter sand. And that product was discarded along history up until the 90s. It was started to be used as a manufactured sand for concrete production as well. However, if you see the PSD of a typical manufactured sand, and in green, and in red you have the standards for fine aggregates in concrete, you see that manufactured sands present a content of particles smaller than 75 micrometers, which is higher than expected. So if you want to use manufactured sands in concrete, you need to extract those particles. So what they do in the quarry is they use a water washing process. So they feed the sand to the washer along fresh water coming from a flooded quarry generally. They mix, they perform a mix in the washer and extract the coarse particles with a screw or a bucket elevator. And the fines, they are mixed with the water and they form a slurry, which is the overflow of the washer. And it ends up being pumped to the flooded quarry again, which acts as a natural decantation system. So the way we saw that this at the time is they are sending fines to the quarry, but they also losing money because these fine particles require a lot of energy to achieve that size. So what about trying to recover those fines and use it and try to see if they have a different technological application in other industries? So there were different solutions at the time provided by dealers like Mezzo or other dealers that they were too costly for the quarry owners. So we tried to develop some more simple designs to replace the water washing process. So we started with very simple models of air classifiers. Just to illustrate here, we have this inclined plate classifier, which is a classifier in which you feed the manufactured sand here, and a very low velocity airflow goes up and extracts the fine particles. So we realized that we do not need a fancy classifier to do this. It's just to dedust the manufactured sand. So a very simple design with a very low energy consumption will do the task. We just need to extract the minimum amount of particles just to push the PSD into the standards. So we tried several designs. We did some CFD simulations coupled with some DPM method. And several iterations later, we came up with this design that we call the throat classifier. And of course, it's quite simple and it is meant to be cheap and robust. You can feed the manufactured sand directly from the atmosphere It doesn't have to be an enclosure. Particles fall to the bottom and bounce again on an inclined plate in which some segregation occurs. Coarse particles are allowed to slide and roll over the fine particles. So in this sliding, coarse particles will have more inertia at the end of the plate compared to the fine particles, which will stick to the plate and present almost zero velocity here. At the end of the plate, there is a space or a region which we call the throat. And we create that throat with a vertical deflector that can move in the horizontal and vertical direction. So we can control the width of the throat. And the throat is the region where the airflow also accelerates. So fine particles with a minimum velocity here can be pushed to the other side of the deflector with a very low stream of airflow, very weak airflow. And when that happens, the airflow in the secondary chamber here decelerates. So particles that were extracted from the sun are allowed to settle in this chamber. And the finest particles can go up with the air and be collected in the auxiliary unit. So the throat classifier has three products. The primary product, which is a manufactured sand with no dust. The dust is the secondary product here. And the tertiary product is the ultrafine particles that we collect in a cyclonic classifier or in a back filter. And there's a video here just to illustrate how it works. You can see here the bigger particles going very fast to the outlet. And fine particles are just pushed to the other side of the deflector. Additionally, this classifier can operate with a secondary airflow, which is just entering in the same region where the coarse particles enter. So it can be used just as a transfer chute if you want. So we built this device and tested in a pilot scale with this configuration in which we have an endless screw feeder and a back filter as an auxiliary equipment. At the time, we had a decent feed rate with 80 kilograms per hour. And we tried with sands with moisture content below 0.3% and very low air velocities, below 10 meters per second. You see here the raw manufactured sands, which I call granite 03, 06, and dolomite 06, tagging the origin of the sand and the top size, which is 3 and 6 millimeters. And you see that the content of dust of each of the sand is way above 5%, which is the maximum allowed by the standard. You have up to 15% of particles below 75 micrometers. And we tested in different configurations of the deflector. We'll just talk about one of the positions of the deflector, which is this one here. And we tested with and without the secondary airflow with different velocities. So just to sum up some of the results here, cases D1 and D2 have the same pressure loss in the classifier, but they have, in D1, we only have the primary airflow, while in D2, we have both the primary and secondary airflow. And you see a large difference in the PSD of the primary product here in both cases. So when you open the secondary airflow, it has a very big impact on the classification. So as you see here, we meet the standards in the D1 and we extracted too much fines in the D2 case. So what we can do is to lower the air velocity now that we have a good classification. And so we did. And we tested several velocities as low as 0.75 meters per second. And we can go from the D2 case to a primary product meeting the standards here with very low velocities. Of course, if you have high velocities, more particles are extracted from the sun and go to the secondary product. So the secondary product gets coarser, and tertiary product as well, because some of the particles go to the back filter. We also tested with different top sizes, granite sand with 6 millimeters and dolomite sand with 6 millimeters. The air classification works, just that this sand is less fit for the standards because it's too coarse. But this part here, if you remove this, the sand will go to the standards after you extract these fines. But that is a task that could be performed with sieving and not with air classification. And in terms of energy consumption, if you compare pressure losses of this classifier with other similar classifiers, you see that it presents quite low pressure loss and very low air velocities. So in terms of energy, it has a great potential. Of course, we model this with CFD and DPM. And you see here two positions of the deflector, P1 and P2, where the throat is different. The width of the throat is different. And you see how primary airflow enters here. And in this case, you have the primary and secondary airflow, and both airflow meets here at the throat. And in this case, the throat is more little. And so the air accelerates way more, and you have a higher velocity here at the throat. So you have some versatility here to use with the deflector, which can be used if you want to use the classifier in other industries. We, of course, validated this with measurement profiles from the throat classifier, giving us good adherence between simulations and experiments. And if you want to pick here the DPM results, you see in case 1 and case 2, they just differ in the opening of the secondary airflow. Case 1 just have the primary airflow, so particles fall, and coarse particles in red go directly to the outlet, primary product outlet. Some blue particles, which are the dust particles, go to the secondary chamber here, and some of them settle in the secondary chamber. When you have the secondary airflow open or being used, you have almost all particles of dust are extracted from the sun. And that is in very good agreement with what we found in the experiments. And more analytically, if you compare the white triangles here, which are the PSD, experimental PSD of the products, and the simulations, you see that for the primary product, you have a very good result. And secondary product, the simulation is given some errors, the tertiary product also. But our main goal was to simulate the primary product, so we were happy. We were happy with the results at the time. Of course, you can refine the simulation in order to have more accurate results of secondary classification that happens in the secondary chamber. And the same here, if you want to compare the mass percentage in the feed of the primary product, you see that it is in good agreement. And also the cut size of the primary classification. On the secondary tertiary product, there are some errors, as well as in the secondary cut size. And as I said, our goal was to simulate the primary product, so our goal was fulfilled, but however, it can be refined. After we have this pilot scale test, we wanted to compare how this classifier worked compared to the washing process. So we went to the quarry and took some samples. So here is the sample that we took, a 0 to 6 millimeters raw sand. And We also have some samples of the water washing product, the washed sand. And we compare this to the primary product of the throat classifier. And you see in the context of fine particles, the sand has almost 10% of dust, and the water washer remove only 6%, while the primary product of the throat classifier have less amount of fines. And we also could collect the secondary and tertiary products in the throat classifier. And in terms of energy consumption, the throat classifier resulted in a less electrical energy usage compared to the water washing process and less CO2 emissions. So despite not using water, it is also more environmental friendly in terms of CO2. And finally, we took this ultrafine product that we collected with the throat classifier and sent it to a partner institute, which is working with polymers. And he injected those particles in cornstarch and created a polymer which resulted in an increased strength and also presented good UV barrier capacities and blocking capacities. So this is just to illustrate how these fine particles could be used in different industries with good applications. And just another quick example of the utilization of this classifier, we also had a client which used tungsten powders in their facilities. And it has two suppliers, the tungsten powder, the green and red. And the red one gave him the better performance in his process. So he wanted us to see if we could use the classifier to transform the green PSD to the red PSD, assuming that the PSD is just what matters in the process. And it was a challenge because tungsten powders had a very different specific gravity compared to the granite or dolomite. And after several tests, we found that at a throw velocity of 4.9 meters per second, this blue line, which is the raw tungsten powder, could be transformed into the black line here, which is the most higher likelihood that we found compared to the red with the target powder. And just to illustrate how this classifier could be used in other type of industries and not to be limited to the aggregate industry. And another project that we are currently in progress right now in Rio de Janeiro is quite similar. I will present today as well, and it is a gravitational inertia classifier. It is a gneiss quarry instead of a granite quarry, in which they have a tertiary crushing scheme, and they have a BSI crusher, which is fed with this coarse aggregate. And the BSI product goes through a double screen deck. The fine product of the screen deck is intended to be used as manufactured sands, and the fine of the sands is intended to be used as filler in the glass industry. So they bought a complete solution from Metso, AC30, and we are giving some guidance and trying to optimize the process with them. Here you see the air classifier, which is mounted right now, the AC30. It goes directly to the back filter. It doesn't have a secondary air classifier. And how does it work? You have here the feed, which is the BSI outlet, and it goes in a cascade manner along with the primary airflow. And both the feed and the primary airflow go in a co-current scheme until a classification region. And here particles can follow the path of the air, which have a very sudden change of direction here to the outlet. So some particles may follow the air, and some others go down to the bottom of the classifier, where they meet a secondary airflow. And the airflow uh, just lift the particles back up to the recirculation region, and then to the classification region again. So the particles have now a second chance of being classified. So the classification process can be tuned with these two air valves here, changing the contribution of the primary and the secondary airflows. We were allowed to play a little bit with this classifier. So we perform a very small central composite design in the industry, changing the valves to the minimum and to the maximum, along with a medium point. So we have a minimum airflow and a maximum airflow case. We did this with a constant fan frequency and a constant feed rate of 100 tons per hour. And we also had a chance to measure the air velocity in the inlet, primary and secondary inlet, and also the pressure losses in the valves and in the overall air classifier. And we did this with and without particles being fed to the classifier. So we have the case in which there is only air in the classifier, and when we have the mixture of air and particles. Let's see some results here. Here we have the total flow rate versus each case and the pressure losses. In white, you have the case where there's only air in the classifier, and in brown, when you have air and particles. Of course, the minimum case is where the minimum flow rate occurs. And here you have the maximum flow rate. In every case, when you put particles, generally, the flow rate decreases. And the opposite is happening here, because pressure loss is the opposite to the flow rate. The minimum case is where the greater pressure loss is happening. The maximum flow rate is where the minimum pressure loss is happening. And here you see how injecting particles in the air classifier create a pressure loss jump in each case. When you put the results in this way, you see that the air-only results are more well-behaved, whereas air-laden flows present more scatter. And I think this could be explained because the back filter is operating and it is being cleaned with a certain frequency. And also you have fluctuations in the feed rates. So you have this scatter here. However, in every case, in the two cases, you can just infer the pressure jump curve of the fan. And in terms of classification, we were expecting cut sizes in the order of 75 micrometers, which was in more agreement, but what is used in the industry. However, there is only one case, which is the maximum flow rate case, that is giving us cut sizes near to 75 micrometers. The other cases present lower flow rates and are giving us finer cut sizes. And the partition curves get quite ugly because of this fishhook effect that I mentioned before. In some cases, you cannot even compute the cut size. So the partition curves are quite messy, and we are performing new iterations of industrial tests to figure out how to optimize the process. This is just an ongoing work, and this is partial results. But of course, we are trying to simulate this as well. We are developing what I call a fast CFD-DPM modeling, in which we want to simulate what's happening inside the classifier, but we do not want to have very large computation times. So in order to achieve this, I reduce the computational domain of the classifier to a slice, eliminating the valves and other non-dominant geometries. And the slice is about 50 millimeters, whereas the whole classifier presents at 3 meters wide width. And for solids, I am using DPM method because it is fast and it can be used in the same CFD solver. But I cannot use the whole PSD of the sun because there are too many sizes and the amount of particles I need to inject in the simulation is too large. So what I did is to go to a coarse graining scheme based on the momentum and mass and volume conservation. So I'm just injecting just one particle size, trying to achieve the same effect of the whole sun going through the classifier. And I call this the bulk particles. And after injecting these particles, the bulk particles, I inject tracer particles with a discretized PSD in order to track the trajectories and compute the partition curve. And to see some results here, you see here the pressure loss versus time simulated time for the 5 cases. And in dashed line, you have the experimental values. You see that when you have only air at the beginning, you have a low pressure loss, which is increased by the presence of the particles. And the same is happening in this fast CFD DPM method. Of course, there are large errors, which we were expecting. And in some cases, the agreement is way better than others. However, we can refine this, but anything that we can do is going to give us larger computation times. And in terms of partition curves, the simulation method is given at coarser cut sizes compared to experimental ones in gray, here for the 5 cases. Not only that, it also is a more ideal solution. So what's happening here is DPM method is not accounting for particle interactions or the volume fraction of the particles inside of the classifier. So in order to have a fast simulation, you need to have some errors. So how can we improve these simulations? Okay, we can just change the coarse graining scheme or use more bulk particle sizes. We can change the boundary condition or include more precise turbulent effects. Or we can even migrate to a full DMM environment. Now there we can consider all particle forces and addition forces and collisions. However, any of these points will present very large computation times compared to what we have now. So just for you to know, one simulation or one case now is taking almost a week. If we go to a DM environment, it could take months to resolve. So just to illustrate here some of these topics, I changed arbitrarily the coarse graining size to half the value. The computed value of the coarse graining size for bulk particles in order to conserve volume and momentum inside of the classifier was 1 millimeter. And I changed it arbitrarily to have this value to 500 micrometers. And you see the results here. So in violet, you have here this results for the coarse graining size of 500 micrometers. And you have an increase in the pressure loss due to the particle presence. And this makes sense because fine particles exchange momentum more efficiently with the air. However, I think this exaggerates the effect of pressure losses. On the other hand, if you check the partition curve in the 2 cases, there is not much change. The red line here with the 500 micrometer bulk particles is given almost the same results. Another way that we can improve, and we are doing it, is to use more specific boundary conditions for the slice domain. In order to do this, I simulated the whole air classifier, the whole classifier, using a symmetry condition at the plane of symmetry. And after I simulated the whole classifier, I extracted specific velocity profiles from the full solution and fed it to the sliced domain. So I can have now this sliced domain simulation with more specific boundary conditions. To have a peak in the result, you have the static pressure and the velocity magnitude for the full case, the full solution, considering the air valves and the air inlet of the to the classifier. And you see how the valves and the air inlets play a role inside the classifier in the airflow and the pressure losses, and also in the creation of turbulence, and how this valve creates turbulence into the flow. So once I extracted these velocity profiles from these solutions and pasted on the size domain, I have this comparison. So here at the left, you have the minimum flow rate case and the maximum flow rate case. And I'm comparing here the first iteration of the fast CFD DPM solver with the second one, considering the more precise boundary conditions with without and with particles inside the classifier. So you can see here how the change in the boundary conditions create more information into the flow, and how turbulent structures are more well represented inside the classifier. And also how this change with the presence of particles here. I did not put the particles just to see the airflow. And you see considerable differences in the airflow without and with the particles. Of course, in the case of maximum flow rate, this is more clearly visible. And also you can see that the falling particles not only create a Corten effect here in the classification region, but it also creates secondary or backflows in the recirculation region, which were not simulated in the first case. Sorry, in the case here. So after I simulated the airflow, I can put the particles inside. And again, I'm comparing the minimum, medium, and maximum flow rate cases with the particles. Here are tracer particles, which are meant to be different sizes, so I can compute the partition curve. And you can see the first iteration here and the second iteration here with more precise boundary conditions. And you see how the trajectories of the particles change, especially the fine particles, which are in blue. Violet particles are the bull particles and are hardly moved by the airflow because they are too coarse. If you see here, you can see where the turbulence occurs inside of the classifier, in the same way that you can spot here the turbulence occurring inside the zigzag classifier with the particle dots. So I think that it is a great improvement compared to the first iteration. However, it is not a fast way anymore because you have to perform a full solution of the classifier to have this more accurate result. In terms of the partition curves, you see here in full dots the improved version compared to the dashed line plots where is the first iteration of the fast CFD DPM method, and compared to the experimental values in gray. So now you have finer cut sizes in more agreement with the experimental values, and you have more imperfection, which also occurs in reality. So there is an improvement in using better boundary conditions for the CFD case. However, there are still a lot of room to improve this technique and to have more accurate and realistic results. So my time's up. So to sum up this presentation, air classification is a tool that is used consistently across multiple industries. It presents a simple operation and design and operation as well. And the performance is defined by the pressure loss, the cut size, and the sharpness of the cut. However, classification mechanisms inside the classifiers are quite complex and mostly due to particle-particle interactions as well as turbulent turbulence inside the classifier. And there are different computational modeling techniques that we can use to have these methods going and obtaining good results. However, you saw that there is a lot of room for improvements, and that's a challenge that we need to address in the near future to have more realistic and accurate simulations for this type of processes. So thanks for the attention. I'm open for questions.
Thank you, Andres, for the very nice presentation, very nice talk. So we have some time for questions. So if you have it, just open the mic and speak up or raise the hand. Feel free to ask questions for this.
Question, Malcolm Powell here.
Hello, Malcolm.
Really enjoyed your presentation. Thank you, and the way you've shown the progression of introducing complexity and how far it may or may not get you, and how you need to get to terms with that when you want to do a real design. I was really interested in your throat classifier, two-stage throat classifier. You showed extremely low velocities and pressure drops. I presume the velocities were at the entrance rather than at the throat, and the pressure drop across the system. There's one point. And the other, do you have an idea of the energy per ton? I think you had it in a small table I couldn't read. So how much energy haven't you put per ton of rock is important in those applications.
Malcolm, thanks for the question. Regarding that question about the energy, it was too small. I'm sorry for that, but it didn't. So the energy, electrical energy used per ton, it was about 2.53 megajoules per ton. And the throat classifier, the velocity was measured at the throat because you have two inlets. You have the one inlet at the top and one inlet at the bottom. You can measure both, and the total airflow you will have here. So the velocity is at the throat, and the pressure loss is just measured at the outlet and compared to the atmosphere pressure, because again, you need to measure two pressures, the pressure at the inlet, primary inlet and the secondary inlet. So they may differ a little bit because of the acceleration of the air from the atmosphere to the inlet. They differ a little bit, but it is more, see, I thought at the time that the best was to see not only how air accelerates inside of the classifier and that creates a pressure loss, but also how air accelerates from the outside to the inside, and that also creates a pressure loss. So measuring just the outlet and comparing to the atmospheric pressure, that gives you the whole picture. That's.
I understand that. Yeah, that's what I was guessing. Yeah, so the throat velocity is really low. 0.75 meters per second is really low for air classification. I was surprised by that.
Yeah, it was very low. Of course, we tested with rather decent feed rates. Of course, if you can increase the feed rates, you may need more velocity. At the time, we didn't have the equipment to do that, and then I moved to Rio, and that stayed silent for a while. Now we are trying to recover this project and to test it with more rigorosity in terms of the feed rates. However, it is very low, and it surprised us as well. And I think it is because of some sort of segregation that occurs in the inclined plate, which could also be studied, because if you put some rugosity device in the inclined plate, I think that could be exaggerated. That segregation could be exaggerated. However, it is a matter of future research. And
Okay.
Other questions? Okay.
Yeah, I would have a question, Horacio. First of all, really exciting results, and I think we did some similar things, of course, with different geometries some 10 years ago, and the idea was to do a four-way coupling, and the thesis after 20 pages became a two-way coupling and then a one-way coupling, because calculation times for four-way coupling were calculated to be years, not only months, as you said. So the question, which I think and is even more important, is how did you cater for the in-stationary processes? Because the pressure drop, as you already correctly mentioned, the pressure drop depends on the particle sizes and on the amount of solids, the solid content in the air. And on the other side, with the pressure drop, the cut size changes, and this influences on the other side with the pressure drop and the content of solids. So you have essentially a highly dynamic process. And if you calculate just on, as you said, you have calculation times of weeks at least, or of a week. Say, how valid do you think it is to expect that sometimes we will see the calculation for the in-stationary processes?
I think, just to see if I understand the question, how much time to have a stationary regime in the...
Yeah, I mean, no, for me, the question is, you never reach a stationary, or it's
No.
absolutely theoretical in my eyes that you reach a stationary regime. So,
Yeah,
which means you
what I
have to
do,
cater for.
yeah, just what I do to try to accomplish that, which cannot be accomplished because time step
Mm.
too large. I mean, you would need several seconds or minutes to achieve a stationary regime. So what I do is just have a few seconds of CFD simulation until pressure drops and flow rates stabilize. Then I inject the bulk particles until again the pressure loss stabilizes. And then I inject the tracer particles, which is very small time steps. I think it's you see in the presentation here. This is a slide which tell you this. Let's see if I can go to that. It's about the whole simulation. It's about 6 seconds in total. You have the CFD solution of 0 to 3 seconds. It's only air. Then you inject the bulk particles for about 3 to 4.5 seconds, which is approximately the double the time that the particles require to fall from the feed inlet to the bottom, double this time. Then you see that pressure losses stabilizes. And then you have a very small step of tracer particles, and then you have a transient regime until at the end you compute where particles are, or how much particles went to the outside of the classifier and where. And then you compute the partition curve. So the total simulation is 6 seconds, and that takes at least a week for now.
Yeah, and for instance, if you have such as the inlet positions of the adjustment of the flaps of the gates here, essentially, you have each of the flaps has a different angle.
Yeah.
Which means you have a control of the air, and what we find in our investigations, also experimental, that the secondary air has a huge impact. But on the other side, the amount, I mean, you have a huge cross section here. Essentially, all the lower, I would say 50% of the cross section is pretty much closed. So it's only the upper flaps which are in the direction of the airflow.
Yes.
Did you calculate this for the different positions of these flaps?
I just measured in the side the positions, and we have access to the classifier, but we do not have full access to the blueprints. So there are lots of things that are inferred in terms of the external geometry, which is tricky because you have the liners and you have some gaps there. So in the full CFD solution, I try to be quite rigorous about the flaps and the position of the flaps. But turns out I can, based on the images and measurement that I had inside and the solutions, I could iterate some errors or some parameters of the angle position versus the flow rates, as you say. However, I could iterate that, but I thought I was creating an artifact and trying to overfit the model.
Okay.
So and the same goes for the internal flaps, the internal plates, which I don't have a total certainty of how the angle and the sizes. So I could iterate that until the pressure losses meet. However, I think that I could be just creating some solution which is not real.
And the last question is about the shape. You just used spherical shapes or also alternative shapes, and the density was all the same of all the particles, or did you have also, or can you cater on your model also for different densities, which is normal and more particular for the final sizes?
For the gravitational classifier, particle shape was measured, and I think was a sphericity of 0.7, some sort near that.
Okay.
And no, biparticles and all particles present the same shape.
Okay.
We do not have evidence that. I mean, fine particles are more flaky usually, so they will present a particle shape which is rather different from the mean, and that could give you a more drag. However, I think that we are not with the precision, enough precision to see that particle shape could be dominant. I think that we have to solve these very large errors first, and then refine the simulation to secondary, I think, mechanism or phenomenon.
Okay, thank you very much.
Thank you.
Right, so we are running out of time, so let's thank you, Andres, again for the very informative talk, very interesting presentation. And if you have any further questions, you can contact Andres, or you can rewatch the recording on the YouTube channel. So congratulations, Andres.
Thank you all for joining. Thank you all. Thank you all. Good morning.
Yes, thanks
a lot.
Thanks a lot.
Cheers, everyone.
Cheers.
Bye, fellas.
Bye.
Cheers. Bye.